Hello and welcome to the Late Lab. Please take a moment to like the video and subscribe to the channel if calm journeys through science are something that help you relax, unwind, or drift gently towards sleep. And while getting comfortable, please feel free to share where this video is being watched or listened to tonight. Perhaps it is playing softly in a quiet bedroom, on a late-night train ride, beside a dim lamp in the living room, or somewhere far across the world where the night has already settled in. Wherever that place may be, it exists within a universe that is far stranger than it appears. The room around you may seem still and empty. The air between objects feels like nothing at all. The space between the walls, between your hands, between every atom of your body appears calm and silent. But modern physics suggests something quite extraordinary. According to our best current understanding of nature, that empty space is not empty at all. In fact, it may be one of the most active and fundamental parts of reality. Invisible structures stretch through every corner of the universe. They pass quietly through your room, through the walls, through the ground beneath you, and even through the atoms that make up your own body. They do not move like ordinary objects, and they cannot be seen directly, yet they are always present. Physicists call them fields, and according to a remarkable framework known as quantum field theory, these fields are not just a feature of the universe, they are the universe. In this strange picture of reality, particles are not tiny solid objects flying through empty space. Instead, every particle that exists may simply be a small ripple in a deeper, invisible field that fills the entire cosmos. An electron is not a tiny bead of matter, it is a vibration in the electron field. A photon, the particle of light, is a ripple in the electromagnetic field, and everywhere in the universe, at every moment, these fields are quietly fluctuating, interacting and shaping the structure of reality itself. Even the space between galaxies, where almost nothing exists, is filled with these unseen layers of physical structure. The idea can feel almost poetic. A universe that appears solid and stable on the surface may actually be more like an immense ocean of invisible fields, where matter itself is nothing more than a pattern of gentle waves. Yet despite how abstract this sounds, quantum field theory is not speculation or philosophy. It is one of the most successful scientific theories ever created. Its predictions have been tested again and again in experiments around the world, from delicate laboratory measurements to enormous particle accelerators stretching beneath the countryside near Geneva. In many cases, its calculations match experimental results with a precision that reaches many decimal places, making it one of the most accurate descriptions of nature ever produced by human minds. But understanding what the theory truly says about reality can feel like stepping into unfamiliar territory. Particles that are not really particles, empty space that is not truly empty, fields that exist everywhere at once, and a universe where the smallest building blocks of matter may simply be vibrations in invisible structures that stretch across all of existence. These ideas did not appear overnight. They emerged slowly over more than a century of discovery, beginning with early hints in 19th century electromagnetism, passing through the strange birth of quantum mechanics, and eventually evolving into the deep and powerful framework known today as quantum field theory. Tonight, the journey will unfold slowly and gently, beginning with the simple question of what empty space really is. The path will gradually move through the history, ideas, and discoveries that led physicists to one of the most remarkable pictures of reality ever imagined. And by the end of this quiet exploration, the universe may feel just a little bit different. because the space around you right now, the quiet air of the room, and the vast darkness between the stars may not be empty at all. Instead, it may be filled with something far more subtle. A universe made not of particles, but of fields. Empty space feels simple. Look around the room for a moment. Between the walls, between the furniture, and between every object in sight, appears to be nothing at all. The air seems calm and quiet, a transparent gap that allows things to exist without touching one another. For most of human history, that is exactly how empty space was imagined, a vast container in which matter sits and moves, a silent stage on which the events of the universe unfold. This view felt perfectly reasonable. After all, if space were filled with something, surely it would be noticeable. Something that filled every corner of the universe should push back, glow, shimmer, or at least leave some obvious trace. Yet the deeper scientists looked into the nature of reality, the more this simple picture began to unravel. The first hints appeared in the 19th century, during the age when electricity and magnetism were being explored with increasing precision. At the time, physicists were trying to understand how forces could act across space. How could a magnet pull on a piece of iron without touching it? How could an electric charge influence another charge some distance away? For centuries, this had been explained using the idea of action at a distance. One object somehow influenced another across empty space, without anything physical connecting them. But a self-taught English scientist named Michael Faraday began to see things differently. Faraday carried out countless experiments with magnets and electric currents, often working with equipment that looked surprisingly simple. Coils of wire, pieces of metal, batteries, and carefully arranged magnets filled his laboratory. Yet from these modest tools came a profound insight. Faraday imagined that space itself might contain invisible structures. When a magnet was placed near iron filings, those filings arranged themselves into delicate curved patterns. Instead of thinking of the magnet as pulling on each tiny piece individually, Faraday suggested that the magnet created a pattern throughout the surrounding space. He called these patterns lines of force. In Faraday's view, space was not simply empty. It was filled with a physical condition that could be shaped by magnets and electric charges. The magnet altered the surrounding region, and that altered region then influenced other objects. It was a radical idea at the time. Many scientists initially treated Faraday's lines of force as helpful diagrams rather than something physically real. Then along came a Scottish physicist named James Clerk Maxwell. Maxwell had an extraordinary ability to translate physical intuition into mathematics. Building on Faraday's ideas, he developed a set of equations that described how electric and magnetic fields behave and interact. These equations revealed something astonishing. Electric and magnetic fields could ripple through space as waves, and those waves moved at a speed that matched the measured speed of light. The conclusion was unavoidable. Light itself was a wave traveling through an electromagnetic field. This discovery changed the meaning of empty space forever. If light could travel through space as a wave, then something had to be waving. There had to be a physical structure spread throughout the universe that could oscillate and carry energy. The electromagnetic field was not just a convenient description. It behaved as though it was something physically real, present at every point in space. For the first time, scientists began seriously considering the possibility that space might contain invisible structures extending everywhere, but the implications went even further. If an electromagnetic field could exist everywhere, then space could carry physical properties even in places where no matter existed at all. A field assigns a value to every location. At one point it might be strong, at another weaker, but it is present everywhere. In other words, physical quantities can exist even in regions that appear empty. By the late 19th century, this idea had started to reshape the foundations of physics. Some scientists began exploring whether the vacuum itself might possess subtle properties. Among them was Ernst Mach, an Austrian physicist and philosopher who deeply questioned the assumptions underlying classical physics. Mach argued that motion and physical laws might depend on the distribution of matter throughout the entire universe. While Mach did not formulate field theory himself, his ideas encouraged physicists to think more carefully about how space and matter might be connected. Around the same time, Hendrik Lorentz in the Netherlands was developing mathematical descriptions of how charged particles interact with electromagnetic fields. Lorentz's work helped clarify how electrons behave inside these fields and laid important groundwork for later theories. The picture emerging from these developments was quietly revolutionary. Space was no longer merely an empty container. Instead, it appeared capable of holding structured physical entities known as fields. These fields could stretch across enormous distances. They could carry energy, transmit waves, and influence matter. And they existed everywhere. Yet even this remarkable discovery turned out to be only the beginning. As physicists continued studying atoms and radiation during the early 20th century, they discovered that the behavior of matter at very small scales was far stranger than anyone had expected. The classical theories of Maxwell and Lorentz, as powerful as they were, could not explain certain experimental results. Light sometimes behaved like a wave, but in other situations it behaved like a particle. Electrons sometimes acted like tiny objects, but under certain conditions they spread out like waves. These strange observations eventually gave birth to quantum mechanics, a theory describing the probabilistic behavior of particles at microscopic scales. But quantum mechanics introduced its own puzzle. If matter behaved like waves, and light behaved partly like particles, what exactly were these things made of? What was truly fundamental? As the 20th century progressed, physicists began to suspect that the old picture of particles moving through empty space might be misleading. Perhaps particles themselves were not the deepest layer of reality. Perhaps something more fundamental existed beneath them. This suspicion slowly led scientists toward a new and powerful idea. Instead of imagining a universe built from tiny solid objects, physicists began considering a different possibility. What if the universe is built from fields, not just the electromagnetic field discovered by Maxwell, but many different fields, each filling the entire cosmos? In this view, what appears to be a particle is not a tiny object at all. It is simply a small ripple or disturbance in an underlying field. An electron would be a vibration in the electron field. A photon would be a vibration in the electromagnetic field. Matter itself would be nothing more than patterns of energy moving through these invisible structures. This idea forms the heart of a theory known as quantum field theory. And if this theory is correct, then the empty space surrounding you right now is anything but empty. Even in the quietest corner of the universe, far from stars, planets, and galaxies, these fields remain present, silent, invisible, yet endlessly active. The room around you may appear calm and still, but according to modern physics, it is filled with a complex landscape of fields quietly extending through every atom, every beam of light, and every region of space, which raises a curious possibility. What appears to be solid matter might not be solid at all. Instead, it may simply be the visible surface of something deeper, a universe woven from fields. The idea of a field did not appear suddenly. It emerged slowly from centuries of puzzling observations about electricity and magnetism, two forces that seemed almost mysterious in their ability to act across empty space. Long before the language of modern physics existed, people had noticed curious effects involving static electricity and magnets. Rubbing amber could attract small bits of dust. Certain stones pulled iron toward them with an invisible influence. These phenomena were fascinating, but for a very long time they were treated as isolated curiosities rather than parts of a unified scientific picture. By the early 19th century, however, scientists had begun studying these forces much more carefully. Instruments had improved, experiments became more precise, and patterns began to emerge. One of the most influential figures during this period was Michael Faraday. Faraday was not trained as a mathematician. In fact, he began his career as a bookbinder's apprentice in London, reading scientific texts while repairing their pages. Through extraordinary dedication and experimental talent, he eventually became one of the most important experimental physicists of his time. Faraday carried out hundreds of experiments involving electric currents, coils of wire, and powerful magnets. What fascinated him most was how these forces seemed to extend outward from their sources. If a magnet was placed beneath a sheet of paper sprinkled with iron filings, the filings arranged themselves into graceful curved patterns. These shapes seemed to trace something invisible in the space around the magnet. Faraday believed those patterns revealed something real. Instead of imagining magnets pulling on objects from a distance through empty space, he proposed that magnets created structures in the surrounding region. Those structures guided the motion of nearby materials. He called these structures lines of force. Each line represented the direction in which a magnetic influence acted. Close to the magnet, the lines were dense and strong. Farther away, they spread out and weakened. Faraday believed these lines were not merely visual aids. He suspected they represented something physically present in space itself. This was a remarkable shift in thinking. For centuries, the dominant view in physics had treated space as a passive background. Forces simply acted across it, often described mathematically but not thought to exist as independent physical structures. Faraday suggested something very different. He imagined space filled with invisible conditions that could store energy and guide motion. When a magnet or electric charge appeared, it altered the surrounding region, creating a pattern that other objects could respond to. In modern language, Faraday was describing what we now call a field. Although Faraday's experimental work was brilliant, his ideas lacked a full mathematical framework. That task would be carried out by another scientist whose talents complemented Faraday's intuition perfectly, James Clerk Maxwell. Maxwell was a Scottish physicist with an extraordinary ability to translate physical concepts into precise mathematical form. During the 1860s, he developed a set of equations describing how electric and magnetic fields behave. These equations unified electricity and magnetism into a single theory known as electromagnetism. Maxwell's equations showed that changing electric fields create magnetic fields, and changing magnetic fields create electric fields. When these changes propagate through space together, they form waves. The mathematics revealed something astonishing. These electromagnetic waves travel through space at a speed that matched the measured speed of light. The conclusion was unavoidable. Light itself was an electromagnetic wave. This discovery transformed the understanding of light from something mysterious into a natural consequence of electromagnetic fields. It also had an extraordinary implication. If light is a wave travelling through space, then something must be waving. In water waves, the surface of the ocean moves up and down. In sound waves, air molecules compress and expand. In the case of light, it was the electromagnetic field itself that oscillated. This meant the electromagnetic field had to exist everywhere, even in regions where no visible matter was present. Space could no longer be considered empty. It contained a field capable of vibrating and carrying energy across enormous distances. Maxwell's original equations were powerful but mathematically complex. Later in the 19th century, an English physicist named Oliver Heaviside helped reformulate them into a simpler and more compact vector form. Heaviside introduced mathematical tools that made the equations easier to apply and interpret, reducing Maxwell's original collection of many equations into the 4 elegant relationships taught in modern physics. These equations describe how electric and magnetic fields behave, interact, and propagate through space. Although their full mathematical form can appear intimidating, the essential message is simple. Electric charges generate electric fields. Moving charges produce magnetic fields. Changing electric fields create magnetic fields. Changing magnetic fields create electric fields. Together, these interactions allow electromagnetic waves to move through space. In spoken form, the central relationship describing the energy carried by an electromagnetic wave can be expressed as energy equals Planck constant multiplied by frequency, a relationship later associated with quantum theory and the particle nature of light. But during Maxwell's time, the focus remained firmly on fields and waves rather than particles. Even so, not everyone immediately accepted the idea that fields were real physical entities. Some physicists believed fields were simply convenient mathematical descriptions. In their view, the true reality lay with particles and forces, while fields were only tools used to calculate interactions. Others believed Faraday and Maxwell had revealed something fundamental about the nature of space itself. These debates continued for decades. At one point, many scientists attempted to explain electromagnetic waves using a hypothetical substance called the luminiferous ether. This invisible medium was imagined to fill all of space and provide the material through which light waves travelled. However, experiments carried out in the late 19th century began undermining the ether concept. One famous experiment conducted by Albert Michelson and Edward Morley attempted to detect the motion of Earth through this supposed medium. Their results found no evidence of such motion. Gradually, physicists began abandoning the ether idea while keeping the field concept intact. The electromagnetic field no longer required a physical medium to support it. Instead, it was understood as a property of space itself. This shift was profound. Fields were no longer secondary effects produced by matter. They became fundamental ingredients of reality. By the end of the 19th century, physics had quietly undergone a transformation. The universe was no longer imagined as a collection of particles moving through empty space. Instead, it appeared increasingly likely that space itself contained structured physical entities capable of carrying energy and transmitting forces. This idea would eventually spread far beyond electromagnetism. Physicists began wondering whether other forces might also be described using fields. Could gravity be a field? Could matter itself arise from fields? These questions lingered as the 19th century gave way to the 20th. At the same time, new experiments involving atoms, radiation, and subatomic particles began revealing strange behaviors that classical physics could not explain. The stage was being set for an even deeper shift. The idea of fields had already changed the way scientists thought about electricity, magnetism, and light. Soon it would reshape the understanding of matter itself. and what began as an attempt to explain magnets and sparks would eventually lead to one of the most remarkable frameworks in modern science. A universe built not from particles alone, but from fields that exist everywhere. By the end of the 19th century, many physicists believed that the great structure of physical law was nearly complete. The theories of Isaac Newton explained motion and gravity. The equations developed by James Clerk Maxwell described electricity, magnetism, and light with extraordinary accuracy. Thermodynamics had clarified how heat and energy behave in physical systems. The universe appeared orderly and understandable. Some scientists even suggested that only minor details remained to be filled in. A few experimental puzzles here and there might require adjustment, but the broad picture of nature seemed firmly established. Then, quietly and somewhat inconveniently, nature began presenting a series of experimental results that refused to fit inside the comfortable framework of classical physics. These puzzles emerged from laboratories studying light, heat, and atoms. At first, they seemed like technical details rather than deep crises, yet each new measurement added another small crack to the existing theory. One of the most famous problems involved something known as blackbody radiation. A blackbody is an idealized object that absorbs all radiation falling upon it, and then re-emits energy depending on its temperature. Physicists studied heated cavities made of metal because they behave very similarly to this ideal case. When the inside of such a cavity is heated, it glows and emits radiation across a range of wavelengths. Careful measurements of this radiation revealed a specific pattern in how energy was distributed among different wavelengths of light. Classical physics attempted to explain this pattern using well-understood ideas from electromagnetism and thermodynamics. However, the predictions quickly ran into trouble. When physicists used classical equations to calculate the energy emitted at very short wavelengths, the result grew larger and larger without limit. According to the theory, a heated object should release enormous amounts of energy in the ultraviolet range. This prediction became known as the ultraviolet catastrophe. The name is dramatic, but the issue was very real. If the classical theory were correct, even a warm object should radiate infinite energy at short wavelengths. Clearly that was not happening. Something was wrong. In the year 1900, a German physicist named Max Planck attempted to solve this problem. Planck approached the issue cautiously, treating the mathematics as a technical challenge rather than a revolutionary moment in physics. He introduced an unusual assumption in order to match the experimental data. Instead of allowing energy to vary smoothly and continuously, Planck proposed that energy could only be emitted or absorbed in discrete packets. These packets became known as quanta. Planck's idea can be expressed through a simple relationship describing the energy carried by radiation. In spoken form, that relationship reads energy equals Planck constant multiplied by frequency. The Planck constant is an extremely small quantity that sets the scale for quantum effects. Its value is roughly 6.6 times 10 to the minus 34 joule seconds, which is so small that quantum behavior remains invisible in everyday life. Planck initially viewed this assumption as a mathematical trick, a temporary device that allowed the theory to match experimental observations, but the idea would soon prove far more significant than he expected. Just a few years later, another physicist examined the behavior of light interacting with metal surfaces. His name was Albert Einstein. In 1905, Einstein studied a phenomenon known as the photoelectric effect. When light shines on certain metals, it can eject electrons from the surface. This process had been observed experimentally, but its behavior puzzled scientists. classical wave theory predicted that increasing the intensity of light should increase the energy of the emitted electrons. After all, stronger waves should carry more energy. Yet experiments showed something different. The energy of the emitted electrons depended not on the brightness of the light, but on its frequency, meaning its color. Low-frequency light could shine as brightly as possible and still fail to release electrons. Higher frequency light, even when faint, could knock electrons free immediately. Einstein realized that this behavior made sense if light arrived not as a continuous wave but as individual packets of energy. Each packet carried energy determined by the same relationship introduced by Max Planck. In other words, light behaved as if it were made of particles. These particles of light would later be called photons. Einstein's explanation was initially controversial because it challenged the wave description of light established by Maxwell's electromagnetic theory. Yet experimental evidence continued supporting the particle interpretation. For his explanation of the photoelectric effect, Einstein would eventually receive the Nobel Prize in Physics. By this point, physicists were facing a deeply unsettling realization. Light seemed to behave both as a wave and as a collection of particles. The classical description of radiation as a smooth electromagnetic field appeared incomplete. While these discoveries were unfolding, other scientists were beginning to explore even more subtle properties of energy. One such figure was Walther Nernst, a German physical chemist who studied thermodynamics and energy at extremely low temperatures. Nernst became interested in the possibility that even completely empty space might contain a residual form of energy. He discussed the idea that the vacuum itself might possess a minimum energy level that could never be removed. This concept later became known as zero-point energy. According to this idea, even when a system is cooled as much as possible, it cannot become perfectly still. Tiny fluctuations remain unavoidable because of the fundamental structure of physical law. Although the full implications of zero-point energy would only become clear decades later, Nernst's discussions hinted at a profound possibility. Empty space might not be truly empty. It might contain underlying energy that persists even in the absence of matter or radiation. Meanwhile, additional experiments continued revealing strange behavior at microscopic scales. Studies of atomic spectra showed that atoms emitted light at very specific frequencies rather than across continuous ranges. Each element produced a unique pattern of spectral lines, like a fingerprint of light. These patterns could not be explained by classical physics alone. Gradually a new picture began to emerge. Energy seemed to come in discrete units. Radiation sometimes behaved like particles. Atoms possessed quantized energy levels. These discoveries collectively suggested that nature might not be continuous in the way classical physics had assumed. Instead, at very small scales, the universe might operate through discrete steps. This idea of quantization slowly began spreading across different areas of physics. Yet the transition was not smooth. Maxwell's theory of electromagnetic fields had been extraordinarily successful. It described light as a continuous wave propagating through space. Engineers relied on it to design telegraph systems, radio transmitters, and electrical technology. The equations worked beautifully. But the growing evidence for energy quanta suggested that the behavior of radiation could not be understood entirely within the classical framework. Attention began to grow. On one side stood the elegant theory of electromagnetic fields developed during the 19th century. On the other side appeared a strange collection of experimental results, hinting that energy might exist in discrete packets. Both pictures seemed correct in certain situations, Yet they did not fit comfortably together. Physicists found themselves standing at the edge of a deeper transformation. The smooth fields described by Maxwell appeared to govern the behavior of light as a wave, but the emerging quantum evidence suggested that those same fields might behave like collections of particles under certain conditions. Reconciling these two descriptions would become one of the greatest challenges in the history of physics, and from that challenge would eventually emerge a new framework, one that blended fields and quanta into a single theory, a theory suggesting that fields themselves might be quantized. As the 20th century began, physicists found themselves in a peculiar situation. Experiments were revealing strange behaviors that classical theories could not explain. Yet the underlying mathematics of nature still seemed beautifully consistent in many other areas. The challenge was not that classical physics had completely failed. Newton's laws still described the motion of planets with impressive precision. Maxwell's electromagnetic theory continued to guide engineers designing radios and electrical systems. The difficulty appeared when scientists looked closely at the smallest building blocks of matter. Atoms, electrons, and radiation behaved in ways that resisted the expectations of classical theory. One of the earliest attempts to understand atomic structure came from a Danish physicist named Niels Bohr. In 1913, Bohr proposed a model of the hydrogen atom that built directly on the emerging idea of quantization. Classical physics predicted that electrons orbiting a nucleus should continuously lose energy and spiral inward. If that were true, atoms would collapse almost instantly. But atoms clearly remained stable. Bohr suggested that electrons could occupy only certain allowed orbits around the nucleus. Each orbit corresponded to a specific energy level, and electrons could jump between these levels by absorbing or emitting light. When an electron dropped from a higher energy level to a lower one, it released energy in the form of a photon. Bohr's model successfully explained the spectral lines of hydrogen, those distinctive colours of light emitted by excited atoms. Each line corresponded to a transition between specific energy levels. Although Bohr's theory worked remarkably well for hydrogen, it was still only a partial solution. The deeper question remained unanswered. Why did electrons obey these strange rules in the first place? A more complete explanation would soon emerge through a series of revolutionary ideas. In the 1920s, a group of young physicists began developing a new mathematical language for describing the microscopic world. Among the most important contributors were Werner Heisenberg, Erwin Schrödinger, and Max Born. Werner Heisenberg took an unusual approach. Instead of attempting to visualize electrons moving through space like tiny planets, he focused only on quantities that could be directly measured. Heisenberg developed a mathematical framework known as matrix mechanics. In this formulation, the behavior of quantum systems was described using arrays of numbers called matrices, which evolved over time according to precise rules. Matrix mechanics successfully predicted the behavior of atomic spectra and other quantum phenomena. However, the mathematics appeared abstract and difficult to interpret physically. Soon afterward, another formulation of quantum mechanics appeared that seemed more intuitive. In 1926, Erwin Schrödinger introduced what became known as wave mechanics. Schrödinger proposed that particles such as electrons could be described by a wave-like quantity known as the wave function. This wave function spread through space and evolved over time according to an equation now called the Schrödinger equation. In spoken form, the basic idea of this equation can be expressed as energy multiplied by the wave function equals the sum of kinetic energy and potential energy acting on the wave function. While the full mathematical details are complex, the essential concept is surprisingly elegant. Instead of treating electrons as tiny objects following precise paths, Schrödinger's theory described them as waves of probability distributed throughout space. Where the wave function was large, the electron was more likely to be detected. Where the wave function was small, the chance of finding the electron decreased. At first, it seemed as though matrix mechanics and wave mechanics were completely different theories. Then physicists discovered something remarkable. Despite their very different mathematical appearances, both approaches produced identical predictions. Matrix mechanics and wave mechanics were simply two different ways of describing the same underlying reality. This realization strengthened confidence that physicists were finally uncovering a deeper layer of nature. But an important question remained. If the wave function described a wave of probability, what exactly did that mean? This question was addressed by the German physicist Max Born. Born proposed that the wave function should not be interpreted as a physical wave in space like a water wave or sound wave. Instead, it represented the probability of finding a particle in a particular location. According to Born's probabilistic interpretation, quantum mechanics does not predict exact outcomes for individual events. Instead, it predicts the likelihood of different possibilities. This idea introduced a profound shift in how scientists understood physical law. Classical physics had been deterministic. If the position and velocity of an object were known, its future motion could be predicted exactly. Quantum mechanics replaced that certainty with probability. The theory could predict how likely an electron was to appear in a particular region, but it could not determine the exact outcome of a single measurement. While this concept felt unsettling at first, repeated experiments confirmed that the probabilistic interpretation matched reality extremely well. Another key insight arrived through the work of Wolfgang Pauli. Pauli introduced a principle that became essential for understanding atomic structure. Known as the Pauli exclusion principle, it states that no two electrons in an atom can occupy the same quantum state simultaneously. This rule might sound technical, but its consequences are enormous. The exclusion principle explains why electrons arrange themselves into distinct shells round atomic nuclei. It determines the structure of the periodic table and ultimately governs the chemical behavior of elements. Without the Pauli exclusion principle, matter as we know it would not exist in its familiar form. Atoms would collapse into far simpler arrangements, and chemistry would be dramatically different. While these discoveries rapidly expanded the power of quantum theory, they also raised deep philosophical questions. What exactly was the wave function describing? Was the probabilistic nature of quantum mechanics a reflection of incomplete knowledge, or was randomness truly built into the laws of nature? Several physicists wrestled with these questions. Among them was Pascual Jordan, a German physicist who contributed significantly to the mathematical development of quantum theory. Jordan helped formalize aspects of quantum mechanics and later played an important role in extending quantum ideas to fields. He also participated in early debates about the interpretation of quantum mechanics, discussions that involved figures such as Niels Bohr and Werner Heisenberg. These debates eventually contributed to what became known as the Copenhagen interpretation. According to this perspective, quantum mechanics does not describe an underlying objective reality in the traditional sense. Instead, it provides a framework for predicting the results of measurements. Reality at the smaller scales appears inherently probabilistic. Despite these philosophical uncertainties, quantum mechanics proved extraordinarily successful in explaining the behavior of atoms. It accounted for atomic spectra, chemical bonding, and the stability of matter. Entire fields of science and technology soon began relying on its predictions. Yet a major challenge remained unresolved. Quantum mechanics described particles such as electrons moving within potential fields. It worked beautifully for atoms and molecules, but did not fully describe the fields themselves. Maxwell's electromagnetic field remained a classical theory. Quantum mechanics could describe particles interacting with that field, yet the field itself was not quantized in the original framework. This limitation created an important gap in the theory. Light sometimes behaved like particles called photons, but Maxwell's equations still treated light as a continuous wave in a classical field. Reconciling these two pictures became one of the central goals of theoretical physics during the early 20th century. Scientists began exploring whether fields themselves might obey quantum rules. If particles could be quantized, perhaps fields could be quantized as well. That possibility would lead physicists toward an entirely new way of understanding matter, radiation, and the structure of the universe. A theory in which the fields themselves become the fundamental ingredients of reality. By the late 1920s, quantum mechanics had proven itself to be an extraordinary tool. It explained the structure of atoms, clarified the behavior of electrons, and helped reveal the hidden rules governing chemistry. The theory described microscopic systems with remarkable accuracy. Yet physicists were beginning to notice that something important was missing. Quantum mechanics worked beautifully when particles moved slowly compared with the speed of light. In those situations, the equations developed by Erwin Schrödinger and Werner Heisenberg produced predictions that matched experiments extremely well. But nature does not limit itself to slow motion. In many physical situations, especially those involving energetic particles or high temperatures, motion approaches the speed of light. When that happens, the laws of physics must obey the rules established by Albert Einstein's theory of special relativity. Special relativity introduced a completely new understanding of space and time. According to Einstein, space and time are not separate entities but parts of a unified structure known as space-time. Events that appear simultaneous in one reference frame may not be simultaneous in another. Time itself can slow down or speed up depending on relative motion. One of the most famous consequences of special relativity is the relationship between energy and mass. In spoken form, Einstein's relationship reads energy equals mass multiplied by the speed of light squared. This simple statement carries enormous implications. It reveals that mass is a concentrated form of energy, and that energy can, under the right circumstances, transform into matter. But when physicists attempted to apply quantum mechanics within a relativistic framework, the mathematics became troublesome. The Schrödinger equation worked well for slow particles, yet it did not naturally incorporate the requirements of special relativity. Attempts to modify it often produce strange results, including negative probabilities which make no physical sense. A deeper theory was clearly needed. One of the scientists who confronted this challenge most successfully was the English physicist Paul Dirac. Dirac possessed a rare combination of mathematical brilliance and physical intuition. In 1928, he developed a new equation designed to describe the behavior of electrons while fully respecting the principles of special relativity. This equation became known as the Dirac equation. In spoken form, its conceptual meaning can be summarized as the total energy of the electron equals the combination of its motion through space and its intrinsic mass, all described in a way consistent with relativity and quantum mechanics. Although the underlying mathematics is intricate, the result was astonishingly elegant. Dirac's equation predicted the behavior of electrons with remarkable accuracy. It also naturally incorporated an intrinsic property of electrons known as spin, which had previously been introduced somewhat mysteriously by Wolfgang Pauli. But Dirac soon noticed something unexpected hidden within his own equation. The mathematical solutions did not describe just one type of electron. They described two. One solution corresponded to the familiar negatively charged electron. The other solution appeared to represent a particle identical in mass, but carrying the opposite electric charge. At first, this result seemed puzzling. No such particle had ever been observed. Yet Dirac took the mathematics seriously. He proposed that nature might contain a mirror counterpart to the electron. A few years later, in 1932, the American physicist Carl Anderson observed exactly such a particle while studying cosmic rays in a cloud chamber. The particle behaved like an electron but carried positive charge. It became known as the positron. Dirac's theory had predicted antimatter. This discovery revealed something profound about the structure of the universe. For every type of particle, a corresponding antiparticle could exist. Matter and antimatter share identical masses but carry opposite charges. When they meet, they can annihilate each other, converting their mass into energy, according to Einstein's relationship between energy and mass. While Dirac's equation successfully unified quantum mechanics with special relativity for electrons, it also hinted at a deeper structure underlying particles themselves. The equation suggested that electrons could not simply be treated as tiny independent objects. Instead, their behavior appeared to arise naturally from a more fundamental mathematical description. Around the same time, other physicists were beginning to explore a related idea. If particles behaved according to quantum rules, perhaps fields could as well. One of the early pioneers in this direction was Pascal Jordan. Jordan worked alongside Max Born and Werner Heisenberg during the development of quantum mechanics. He played an important role in extending quantum ideas beyond particles to the electromagnetic field itself. In the late 1920s, Jordan and collaborators proposed that the electromagnetic field could be quantized. Instead of behaving as a perfectly continuous wave, the electromagnetic field would possess discrete energy levels. These quantized excitations corresponded precisely to the particles of light that Albert Einstein had earlier proposed. In other words, photons could be understood as small packets of energy within the electromagnetic field. This insight was revolutionary. Rather than treating particles and fields as separate categories, physicists began realizing that particles might simply be manifestations of fields. Imagine the surface of a calm ocean. The water itself forms a continuous medium stretching across great distances. When a wave appears, it does not represent a separate object floating above the ocean. It is simply a temporary pattern moving through the water. In a similar way, a particle might be understood as a localized disturbance in a field that extends throughout space. An electron would be a ripple in the electron field. A photon would be a ripple in the electromagnetic field. In this picture, the universe is not built primarily from tiny objects moving through empty space. Instead, it is built from fields that exist everywhere, with particles appearing as brief excitations of those fields. This concept gradually transformed how physicists thought about matter. The traditional image of particles as tiny solid spheres began fading away. In its place emerged a more subtle vision of reality. Fields filled all of space. Particles were simply the smallest detectable vibrations within those fields. Although this idea was still developing, it offered a promising path toward resolving several theoretical puzzles. It allowed quantum mechanics, relativity, and field theory to begin merging into a single coherent framework. This emerging framework would soon become known as quantum field theory, and with it came a remarkable shift in perspective. What once seemed like empty space might actually be the most fundamental ingredient of the universe. Imagine standing beside a calm lake on a windless evening. The surface of the water appears smooth and still, stretching outward in every direction. Then a small stone touches the surface, and ripples spread outward in widening circles. Those ripples move across the lake, carrying energy with them, yet the water itself remains in place. The wave is not a separate object floating above the lake. It is simply a pattern moving through the water. This image captures the central idea behind one of the most important insights in modern physics. According to quantum field theory, the universe behaves in a surprisingly similar way. Instead of a lake, imagine that all of space is filled with invisible fields. These fields exist everywhere at once. They stretch across galaxies, through the empty regions between stars, and even through the atoms in your own body. Each type of fundamental particle corresponds to its own field. There is an electron field. There is an electromagnetic field. There are fields associated with quarks, neutrinos, and other particles that physicists have discovered. These fields are not confined to particular locations. They fill the entire universe continuously, assigning values to every point in space and time. Most of the time, these fields appear calm, much like the still surface of that lake. But when energy disturbs a field in a particular way, a small ripple can form. That ripple behaves exactly like a particle. This idea represents a profound shift in perspective. For centuries, matter was imagined as being composed of tiny solid objects moving through empty space. Atoms were once thought to be miniature versions of planetary systems, with electrons orbiting a central nucleus like planets around the Sun. Quantum field theory replaces that theory. Picture with something more subtle. Particles are not tiny objects in the traditional sense. They are localized excitations of underlying fields. Consider the example of light. In classical physics, light was described as an electromagnetic wave moving through space. Maxwell's equations showed that oscillations of electric and magnetic fields propagate together as waves traveling at the speed of light. Quantum theory later revealed that light can also behave as particles called photons. Quantum field theory provides a way to unify these two pictures. The electromagnetic field fills all of space. When that field oscillates in a particular localized way, a photon appears. A photon is therefore not a small, solid particle flying through the universe like a tiny bullet of light. Instead, it is a small bundle of energy moving through the electromagnetic field. The field itself is the fundamental entity. The photon is simply the smallest detectable ripple within it. The same idea applies to electrons. There exists a field known as the electron field that extends throughout the entire cosmos. Whenever energy excites this field in a specific way, an electron appears. That electron behaves as a particle when it interacts with other systems or is detected in experiments. Yet in the deeper theoretical description, it is a localized disturbance traveling through the electron field. One of the most fascinating consequences of this framework involves the identical nature of particles. Every electron in the universe is exactly the same. An electron inside a distant galaxy behaves identically to an electron inside the atoms of your body. They have precisely the same mass, the same electric charge, and the same quantum properties. In the older picture of physics, this identical nature might seem mysterious. Why should every particle be perfectly identical to every other one? Quantum field theory provides a simple explanation. All electrons are excitations of the same underlying field. Just as every wave on a lake arises from the same body of water, every electron arises from the same electron field. The field itself guarantees that each excitation shares identical properties. The electron field does not produce slightly different electrons in different places. It always produces the same type of excitation. This idea helps explain one of the deepest regularities in nature. Matter behaves consistently because the underlying fields are consistent. The shift from particles to fields required physicists to rethink some of their most basic assumptions. Instead of asking where particles are located, the theory asks how fields behave across space and time. Mathematically, these fields obey equations that determine how excitations form, move, and interact. In spoken form, the fundamental relationship connecting energy and mass can be expressed as energy equals mass multiplied by the speed of light squared. This relationship, introduced by Albert Einstein, reminds us that mass itself is a form of energy. Within the framework of quantum fields, that energy becomes organized into stable patterns that appear as particles. Matter is therefore not something separate from energy. It is energy arranged in specific configurations within fields. These ideas were further explored and expanded by several important physicists during the 20th century. Among them was Lev Landau, a Soviet physicist known for his deep insights into many body systems and quantum theory. Landau made major contributions to the study of condensed matter, physics, superfluidity, and the behavior of interacting quantum systems. Although his work often focused on materials such as liquid helium, the conceptual tools he developed helped clarify how collective behavior can emerge from underlying quantum structures. Landau's work showed that complex physical phenomena often arise from the interactions of many small excitations within a field or medium. This perspective reinforced the broader understanding that particles are not isolated objects. Instead, they represent patterns within a deeper physical framework. From this viewpoint, the universe resembles an enormous tapestry woven from overlapping fields. The electron field stretches everywhere. The electromagnetic field fills the cosmos. Other fields exist as well, some associated with particles that are difficult to observe directly, but nonetheless play crucial roles in the structure of matter. Whenever one of these fields is disturbed in the right way, a particle appears. When the disturbance fades, the particle disappears. The field itself remains. This realization transforms the meaning of matter. Instead of thinking of matter as solid substance occupying space, it becomes more accurate to think of matter as energy organized into stable ripples within invisible fields. Even the atoms that form everyday objects are mostly empty space, with electrons existing as quantum excitations around atomic nuclei. The deeper you look into matter, the more it begins to resemble patterns moving through underlying fields, and the quiet space surrounding you right now, which appears so calm and empty, may in fact be filled with those fields extending in every direction. If particles are ripples in fields, then a natural question follows. How do those ripples interact with one another? Why does an electron feel the presence of another electron nearby? How can light push on matter? And how does energy move between particles that appear separated in space? Quantum field theory answers these questions in a beautifully consistent way. Interactions between particles are really interactions between fields. Each field permeates the universe continuously. When one field changes or oscillates, it can influence another field occupying the same region of space. The ripples within those fields can then exchange energy and momentum. In simple terms, Particles interact because their underlying fields interact. Consider the familiar case of electric charge. Electrons carry negative electric charge, which means they interact strongly with the electromagnetic field. When an electron moves, it disturbs the electromagnetic field around it. That disturbance travels outward and can influence other charged particles. Within the framework of quantum field theory, this interaction is described through the exchange of photons. Photons are the smallest excitations of the electromagnetic field. When two charged particles interact, they can exchange photons that carry energy and momentum between them. These photons do not necessarily behave like beams of visible light. Often they are temporary disturbances in the electromagnetic field that exist only briefly during the interaction, but their role is essential. The electromagnetic force between charged particles arises from the exchange of these photon excitations within the field. Developing the mathematical description of these interactions became one of the major achievements of 20th century physics. The resulting theory became known as quantum electrodynamics, often shortened to the acronym QED. Quantum electrodynamics describes how electrons, photons, and the electromagnetic field interact according to the rules of quantum mechanics and special relativity. Several physicists played crucial roles in building this theory during the 1940s. Among the most influential were Richard Feynman in the United States, Julian Schwinger also in the United States, and Shinichiro Tomonaga in Japan. Each of these scientists developed methods for calculating how quantum fields interact. Richard Feynman approached the problem with remarkable creativity. Instead of focusing only on complex equations, he introduced a visual language that allowed physicists to picture interactions between particles. These visual tools became known as Feynman diagrams. A Feynman diagram represents the interaction between particles as a simple drawing. Lines represent particles moving through space-time, while points where lines meet represent interactions between fields. For example, one line might represent an electron moving forward in time. At some point along its path, the electron emits a photon. The photon then travels briefly before being absorbed by another electron. Although these diagrams appear simple, they encode detailed mathematical information about the interaction. Each line and vertex corresponds to a precise contribution to the probability that a particular event will occur. Physicists can use these diagrams to calculate how likely it is for electrons to scatter, emit photons, or interact in other ways. Julian Schwinger developed a more formal mathematical approach that relied on operator methods and advanced quantum equations. Shinichiro Tomonaga independently developed a related formulation that treated quantum fields in a fully relativistic framework. At first glance, these different methods appeared unrelated, yet in 1949 a young physicist named Freeman Dyson carefully analysed the work of Feynman, Schwinger, and Tomonaga. Dyson demonstrated that their theories were actually equivalent. Despite their different mathematical styles, they described the same underlying physical processes. Dyson's work unified these approaches and helped establish quantum electrodynamics as a coherent and powerful theory. With these tools in place, physicists began calculating the outcomes of experiments with astonishing precision. One of the most famous examples involves a property of the electron known as its magnetic moment. The electron behaves somewhat like a tiny magnet, and quantum electrodynamics predicts slight corrections to the strength of this magnetism due to interactions with the electromagnetic field. When physicists calculate these corrections using Feynman diagrams and quantum electrodynamics, the results match experimental measurements with extraordinary accuracy. In some cases, the agreement reaches more than 10 decimal places. To give a sense of scale, this level of precision is comparable to predicting the distance between two cities and being correct within the width of a human hair. Such accuracy is rare in science. It demonstrates that the underlying theory captures the behavior of nature with remarkable fidelity. Experiments carried out in laboratories around the world, including those at institutions such as the National Institute of Standards and Technology and the European Organization for Nuclear Research, have repeatedly confirmed the predictions of quantum electrodynamics. Because of this success, quantum electrodynamics is widely regarded as one of the most accurate scientific theories ever constructed. Yet the deeper significance of the theory lies not only in its precision. Quantum electrodynamics shows how fields communicate with one another. Particles exchange energy through the excitations of fields. Forces arise from the interactions of those fields. What appears to be a simple push or pull between objects is actually a complex exchange of energy, carried by quantum excitations. This perspective reveals a universe woven from interactions between invisible structures. Electrons are excitations of the electron field. Photons are excitations of the electromagnetic field. And when those fields interact, the ripples within them exchange energy in ways that produce the forces we observe. The elegance of this framework lies in its unity. Instead of treating forces as mysterious influences acting across empty space, quantum field theory describes them as the natural consequence of interacting fields. What once seemed like separate phenomena now appear as different aspects of the same underlying structure. The language of fields provides the grammar of these interactions, and with that language, physicists gained the ability to describe nature with astonishing clarity and precision. One of the quiet, guiding principles behind modern physics is something that might at first sound almost artistic rather than scientific: symmetry. In everyday life, symmetry usually brings to mind images of balanced shapes: a butterfly with matching wings, snowflakes with repeating patterns, a circle that looks the same no matter how it is rotated. In physics, the idea of symmetry carries a deeper meaning. A symmetry describes a transformation that leaves the laws of nature unchanged. Imagine performing an experiment today and repeating it tomorrow under the same conditions. The results should not depend on the day of the week. Nature behaves the same way over time. That simple idea represents a symmetry known as time translation symmetry. Likewise, the laws of physics do not depend on where an experiment takes place. Whether it is carried out in a laboratory in Geneva, Tokyo, or Cape Town, the underlying rules remain the same. This reflects a symmetry known as spatial translation symmetry. Even rotating an experiment in different directions should not alter the laws of physics. This property is called rotational symmetry. For a long time, these symmetries were treated as convenient observations about nature. They seemed reasonable and elegant, but their deeper significance remained unclear. Then, in the early 20th century, a remarkable mathematical insight revealed that symmetries were far more powerful than anyone had imagined. This insight came from a German mathematician named Emmy Noether. Noether developed a theorem that established a precise connection between symmetries and conservation laws. Her work showed that whenever a physical system possesses a continuous symmetry, a corresponding physical quantity must remain conserved. The relationship is profound. If the laws of physics do not change over time, then energy must be conserved. If the laws of physics remain the same in every direction in space, then angular momentum must be conserved. If the laws of physics are identical in every location, then linear momentum must be conserved. In spoken form, one of the central conservation relationships that arises from symmetry can be expressed as the total energy of a closed system remains constant over time. Noether's theorem transforms symmetry from a mathematical curiosity into a foundational principle of physics. Conservation laws were no longer separate assumptions added to theories. They emerged naturally from the symmetries embedded in the laws of nature. As physicists continued developing quantum field theory, symmetry began playing an even more central role. One particular type of symmetry turned out to be especially important. This idea is known as gauge symmetry. Gauge symmetry involves transformations that change certain mathematical descriptions of fields while leaving the physical outcomes unchanged. At first, this concept may sound abstract, yet it can be understood through a simple analogy. Imagine describing the height of mountains relative to sea level. Another scientist might choose a different reference point, perhaps measuring height relative to a valley floor instead. The numbers would change, but the physical mountains would remain exactly the same. Gauge symmetry works in a somewhat similar way. Certain mathematical descriptions of fields can shift or transform without altering the observable behavior of nature. In quantum field theory, these transformations are not merely optional mathematical tricks. They impose strict constraints on how fields can behave and interact. Remarkably, requiring gauge symmetry automatically leads to the existence of force-carrying particles. The electromagnetic force, for example, arises from a gauge symmetry associated with the electromagnetic field. The particle that carries this interaction is the photon. As physicists explored these ideas more deeply during the middle of the 20th century, they discovered that gauge symmetry could be extended far beyond electromagnetism. In the year 1954, two physicists named Chen-Ning Yang and Robert Mills introduced a new type of gauge theory. Their work described what became known as non-abelian gauge symmetry. In these theories, the mathematical transformations involved do not simply commute in a straightforward way. Instead, the order of operations matters, creating a richer and more complex structure. Although the mathematics was challenging, the implications were extraordinary. Yang and Mills had discovered a framework capable of describing entire families of interacting fields. Within this framework, forces arise naturally from symmetry principles rather than being inserted by hand. The structure of the symmetry itself determines how particles interact and what types of force carriers must exist. Over time, physicists realized that the fundamental forces of nature might all emerge from different gauge symmetries. Electromagnetism arises from one type of gauge symmetry. The weak, nuclear force, responsible for processes such as radioactive decay, arises from another. The strong nuclear force, which binds quarks together inside protons and neutrons, arises from yet another symmetry structure. Each of these forces can be described using a quantum field theory built around specific gauge symmetries. In this way, symmetry became the mathematical backbone of modern particle physics. Rather than starting with a list of particles and forces, physicists began constructing theories by asking a different question. What symmetries does nature obey? Once those symmetries are identified, the properties of particles and their interactions often follow automatically. It is a bit like discovering the rules of a game and realizing that the entire strategy of the game flows naturally from those rules. This perspective transformed how scientists approached the fundamental laws of the universe. Instead of imagining nature as a collection of separate forces acting independently, physicists began seeing a deeper structure governed by symmetry principles. Fields interact according to rules encoded in these symmetries. Particles appear as excitations within those fields. Forces arise from the exchange of quanta dictated by gauge symmetry. Gradually, these ideas began merging into a unified framework describing the fundamental building blocks of matter. This framework would eventually become known as the Standard Model of Particle Physics. And at its heart lies a simple yet powerful principle. The universe may be governed not only by matter and energy, but by symmetry. As the ideas of quantum fields and symmetry matured during the middle of the 20th century, physicists began assembling a much larger picture of how the smallest building blocks of nature might fit together. Individual discoveries had already revealed many different particles. Electrons were known to exist. Photons carried light. Protons and neutrons formed atomic nuclei. Later, experiments uncovered a growing collection of additional particles emerging from high-energy collisions. At first, the list seemed almost chaotic. New particles appeared in laboratory experiments and cosmic ray detectors, sometimes with strange properties and very short lifetimes. Physicists jokingly refer to this growing catalogue as a particle zoo. The challenge was to determine whether these particles represented unrelated curiosities or whether a deeper pattern connected them. Over time, a remarkable framework began to emerge. This framework eventually became known as the Standard Model of Particle Physics. The Standard Model is not a single equation or a single discovery. Instead, it is a carefully constructed theoretical structure that organizes fundamental particles and the forces acting between them. At its foundation lies the language of quantum field theory. In this framework, every particle corresponds to an excitation of a field that fills the universe. The Standard Model identifies which fields exist, how they interact, and how their excitations appear as the particles detected in experiments. Within this picture, the known fundamental particles fall into several broad categories. One category contains the particles that make up matter itself. These particles are called fermions. Fermions include two important families known as quarks and leptons. Leptons are relatively familiar because one of them is the electron, a particle essential for the structure of atoms. Electrons orbit atomic nuclei and determine the chemical behavior of elements. Alongside the electron are other leptons such as the muon and the tau, which are heavier relatives of the electron. There are also three types of neutrinos, extremely light particles that interact only very weakly with matter. Neutrinos are produced in enormous numbers inside stars and during nuclear reactions. Trillions of them pass through the Earth and through our own bodies every second without leaving noticeable traces. Quarks form the second major group of matter particles. Unlike electrons, quarks do not appear individually in nature under normal conditions. Instead, they combine to form composite particles such as protons and neutrons. Protons and neutrons together make up the nuclei of atoms, meaning quarks lie at the heart of the ordinary matter that forms planets, stars, and living organisms. The idea that protons and neutrons might contain smaller constituents emerged during the 1960s. Two physicists played central roles in developing this insight. One was Murray Gell-Mann in the United States. The other was George Zweig, working independently at the same time. Both proposed that the growing collection of strongly interacting particles could be explained if protons, neutrons, and similar particles were built from smaller components. Gell-Mann called these components quarks. The quark model successfully organized many particles that had previously seemed unrelated. Protons and neutrons were understood as combinations of three quarks bound together. For example, a proton contains two up quarks and one down quark, while a neutron contains one up quark and two down quarks. Although the quark model initially appeared speculative, Later experiments confirm that quarks behave as real constituents within protons and neutrons. However, quarks possess an unusual property: they're never observed alone. Whenever physicists attempt to separate quarks, the energy involved simply produces new quark pairs rather than isolating individual ones. This behavior arises from the force that binds quarks together. That force is known as the strong nuclear force. The quantum field theory describing this interaction is called quantum chromodynamics. The word chromodynamics comes from the Greek word for color, though this color has nothing to do with visible light. Instead, it refers to a property of quarks that governs how they interact through the strong force. Quantum chromodynamics describes how quarks exchange particles known as gluons. Gluons are excitations of the gluon field and act as the carriers of the strong nuclear force. This interaction binds quarks together so tightly that they remain confined inside larger particles. While quarks and leptons represent matter particles, another category of particles plays a different role. These particles are known as gauge bosons. Gauge bosons act as carriers of the fundamental forces. Photons carry the electromagnetic force. Gluons carry the strong nuclear force. Additional particles known as the W boson and the Z boson carry the weak nuclear force. The weak force governs processes such as radioactive decay and plays an essential role in nuclear reactions inside stars. During the 1960s, physicists began searching for a unified theory that could describe both electromagnetism and the weak nuclear force within a single framework. 3 scientists made particularly important contributions to this effort. Sheldon Glashow first proposed a mathematical model that linked these forces through a shared symmetry structure. Later, Abdus Salam and Steven Weinberg independently developed related theories that incorporated the mechanism required to give certain particles mass. Their work showed that the electromagnetic force and the weak nuclear force could be understood as 2 aspects of a single interaction known as the electroweak force. At very high energies, these forces behave as different manifestations of the same underlying field structure. At lower energies, the symmetry becomes hidden, causing the forces to appear distinct. Experiments carried out in particle accelerators during the late 20th century confirmed the existence of the W boson and the Z boson, providing strong evidence for the electroweak theory. Together with quantum chromodynamics, this theory forms the central structure of the Standard Model. What makes the Standard Model especially remarkable is that it is entirely built using quantum field theory. Every particle within the model arises as an excitation of a corresponding field. Every force emerges from interactions between those fields governed by symmetry principles. Matter itself becomes a pattern of excitations moving through the quark and lepton fields. Forces arise from the exchange of gauge bosons between those excitations. The result is a coherent description of the known fundamental particles and 3 of the 4 fundamental forces of nature. Despite its complexity, the Standard Model has achieved extraordinary success in predicting experimental results. Yet even this impressive framework is not the final story. While it explains a vast range of phenomena, it leaves several deep questions unanswered. Those questions continue to guide physicists as they search for an even deeper understanding of the universe. Among all the invisible structures described by modern physics, one field plays an especially intriguing role in shaping the physical world. It is known as the Higgs field. Unlike familiar objects, the Higgs field is not confined to a particular region of space. It does not form clouds, waves on the ocean, or streams of particles moving from one place to another. Instead, it exists everywhere at once. The Higgs field fills the entire universe. It stretches across galaxies, across the quiet spaces between stars, and through every atom of every object around you. Even in the most remote regions of intergalactic space, where matter is almost absent, the Higgs field remains present. This idea may sound unusual, but within the framework of quantum field theory, it is perfectly natural. Many fields extend throughout the cosmos. The electromagnetic field does this. The electron field does as well. The Higgs field belongs to that same family of universal structures. Yet the Higgs field possesses a special property that makes it unique among the fields described in the Standard Model of Particle Physics. It is responsible for giving many fundamental particles their mass. To understand why this is remarkable, it helps to recall that the equations governing the Standard Model originally describe particles as if they were massless. In the early mathematical formulations, particles such as electrons and the carriers of the weak nuclear force behaved as though they moved at the speed of light. But this clearly does not match reality. Electrons have mass. So do many other particles. Something in the universe must be responsible for creating that mass. The explanation arises from a process known as the Higgs mechanism. The Higgs mechanism describes how particles interacting with the Higgs field acquire mass as a result of that interaction. An analogy can make this idea easier to visualize. Imagine walking through a large crowded room. If the room were completely empty, you could move freely and quickly from one side to the other. Nothing would slow you down. Now imagine that the room is filled with people. As you move through the crowd, your motion becomes more difficult. Conversations begin, attention gathers around you, and the crowd resists your movement. In this analogy, the crowded room represents the Higgs field. Particles that interact strongly with the Higgs field experience resistance when they move through it. That resistance appears as mass. Particles that interact weakly with the field move more freely, and therefore possess smaller masses. Some particles, such as photons, do not interact with the Higgs field at all. As a result, they remain massless and travel at the speed of light. While this analogy is imperfect, it captures the central idea. Mass does not necessarily arise from something contained inside particles themselves. Instead, it can emerge from interactions with an underlying field that fills all of space. The theoretical foundations of this idea were developed during the 1960s by several physicists working independently. Among the most important contributors were Peter Higgs in the United Kingdom, François Englert and Robert Brute in Belgium, and other researchers including Gerald Guralnick, Carl Hagen, and Tom Kibble. These scientists were exploring how gauge symmetry, a key principle of quantum field theory, could remain mathematically consistent while still allowing particles to possess mass. Their solution involved introducing a new field with unusual properties. This field would possess a non-zero value even in empty space. Instead of vanishing in the vacuum, the field would maintain a constant background presence throughout the universe. Particles interacting with this background field would then acquire mass naturally through their interactions with it. The theory predicted that the Higgs field should produce a corresponding particle known as the Higgs boson. This particle would represent a localized excitation of the Higgs field, similar to how photons arise from the electromagnetic field. Detecting the Higgs boson became one of the most important goals of modern particle physics. However, observing it required extremely high energies. Producing a Higgs boson demands conditions similar to those present in the early universe, when temperatures and energies were far greater than those found on Earth. To reach those energies, scientists constructed enormous particle accelerators. The most powerful of these machines is the Large Hadron Collider located near Geneva, on the border between Switzerland and France. This facility is operated by the European Organisation for Nuclear Research, commonly known as CERN. The Large Hadron Collider accelerates protons to energies of several trillion electron volts and then brings them into head-on collisions. These collisions briefly recreate conditions similar to those that existed a fraction of a second after the Big Bang. When protons collide at such enormous energies, their internal quarks and gluons interact in complex ways. Occasionally, these interactions produce new particles predicted by theoretical models. For many years, physicists searched for signs of the Higgs boson within the debris of these collisions. Finally, in the year 2012, two large experimental collaborations at CERN, known as ATLAS and CMS, announced the discovery of a new particle with properties consistent with the Higgs boson. The particle had a mass roughly 125 times greater than the mass of a proton. Its behavior matched the predictions made by the Higgs mechanism decades earlier. The discovery represented one of the most significant achievements in modern physics. It confirmed that the Higgs field exists and that the mechanism proposed by Higgs, Englert, Brute, and their colleagues accurately describes how particles acquire mass. For this work, François Englert and Peter Higgs were awarded the Nobel Prize in Physics in 2013. The discovery of the Higgs boson also reinforced a deeper lesson about the nature of reality. Empty space is not empty. Even when no particles are present, the Higgs field remains. It fills the vacuum with structure. Particles moving through that vacuum interact with the field and acquire properties such as mass. In other words, the vacuum itself possesses physical characteristics. Space is not merely a passive stage where matter happens to exist. Instead, it contains fields that actively shape the behavior of particles and forces. The Higgs field provides one of the clearest examples of this idea. What appears to be empty space around you right now may contain a quiet but powerful structure influencing the properties of every particle in the universe. The mass of the atoms in your body, the stability of matter, and the structure of the physical world all depend on interactions with a field that cannot be seen directly. A field that fills the cosmos silently and continuously, and yet its presence can be detected through the particles that briefly emerge from it during high-energy collisions. In that sense, the Higgs field stands as a reminder that the deepest structures of the universe are often hidden beneath the surface of what we see. Even the emptiest regions of space may contain layers of invisible order shaping the fabric of reality itself. At first glance, the vacuum seems like the simplest concept in physics. Remove all matter, remove all radiation, and what remains should be nothing at all. An empty region of space. For many centuries, that assumption felt perfectly natural. If a container were evacuated of air and cooled until no visible activity remained, it appeared reasonable to conclude that the space inside contained absolutely nothing. Yet quantum field theory tells a very different story. According to modern physics, the vacuum is not truly empty. Instead, it represents the lowest possible energy state of all the quantum fields that fill the universe, and those fields never become completely still. Even in the quietest possible vacuum, fields continue to fluctuate. This behavior arises from one of the most fundamental principles in quantum mechanics, the uncertainty principle developed by Werner Heisenberg. The uncertainty principle states that certain pairs of physical quantities cannot both be known with perfect precision at the same time. One familiar version involves position and momentum, but the principle also applies to energy and time. In spoken form, this relationship can be expressed as the uncertainty in energy multiplied by the uncertainty in time must be greater than or roughly equal to the reduced Planck constant. The important implication is that energy cannot remain perfectly constant over extremely short intervals of time. For brief moments, small fluctuations in energy are allowed by the laws of quantum mechanics. When this principle is applied to quantum fields, it leads to a remarkable conclusion. Even in a perfect vacuum, fields cannot remain completely quiet. Tiny fluctuations must always occur. These fluctuations are known as vacuum fluctuations. Instead of being a featureless emptiness, the vacuum behaves like a restless sea of microscopic activity. Fields briefly rise and fall in energy, producing momentary disturbances that flicker in and out of existence. One way physicists describe these disturbances is through the idea of virtual particles. Virtual particles are temporary excitations that appear as pairs of particles and antiparticles within these vacuum fluctuations. For extremely short intervals of time, these pairs can exist before quickly annihilating each other and returning their borrowed energy to the vacuum. They are called virtual because they cannot be observed directly as free particles moving through space. Instead, they appear as intermediate steps in the mathematical description of quantum field interactions. Despite their fleeting nature, virtual particles have measurable consequences. Their presence subtly influences how fields behave and how particles interact. One of the most fascinating experimental demonstrations of vacuum fluctuations involves an effect predicted in 1948 by a Dutch physicist named Hendrik Casimir. Casimir considered what would happen if two perfectly conducting metal plates were placed extremely close together in a vacuum. At first, this might sound like an ordinary arrangement of metal surfaces, but the presence of the plates alters the behavior of the electromagnetic field between them. Quantum field theory predicts that vacuum fluctuations of the electromagnetic field occur everywhere. However, when two plates are placed very close together, only certain wavelengths of fluctuations can exist between them. Outside the plates, the full range of fluctuations remains possible. This difference creates a small imbalance in energy. The vacuum fluctuations outside the plates exert slightly greater pressure than the fluctuations between them. As a result, the plates experience a tiny force pushing them together. This phenomenon is known as the Casimir effect. Although the force involved is extremely small, it has been measured experimentally with impressive precision. Modern experiments using sensitive instruments have confirmed that this force behaves exactly as predicted by quantum field theory. The Casimir effect demonstrates something profound. The vacuum itself exerts physical influence. What once seemed like empty space actually contains measurable energy and structure. Another remarkable aspect of vacuum fluctuations involves how they influence the properties of particles. When an electron moves through space, it does not travel through a perfectly empty environment. Instead, it moves through a fluctuating background of quantum fields. These fluctuations slightly alter the electron's behavior. They affect quantities such as its magnetic properties and the way it interacts with electromagnetic radiation. Physicists can calculate these subtle effects using quantum electrodynamics, the quantum field theory describing interactions between electrons and photons. The resulting predictions match experimental measurements with astonishing precision, confirming that the vacuum truly behaves as a dynamic physical system. The concept of vacuum energy also appears in cosmology, where it may play a role in shaping the expansion of the universe. Some physicists associate vacuum energy with the cosmological constant, introduced by Albert Einstein in his equations describing gravity. Observations of distant galaxies suggest that the expansion of the universe is accelerating, and vacuum energy may contribute to this effect. Although the exact relationship remains an area of active research, the possibility highlights how the properties of empty space may influence the behavior of the entire cosmos. The quantum vacuum, therefore, represents much more than an absence of matter. It is the lowest energy configuration of all the fields that permeate space. Those fields never become completely still. Instead, they continue fluctuating at extremely small scales, producing a subtle background of activity even in regions where no particles are present. If it were somehow possible to observe the vacuum directly, it would not appear as a silent void. It would resemble a constantly shifting landscape of tiny disturbances, with fields rising and falling in energy for unimaginably brief moments. This restless character of the vacuum reinforces a theme that has appeared again and again throughout modern physics. What seems empty often contains hidden structure. Space itself possesses properties. Fields extend throughout the universe. And even in the deepest vacuum imaginable, the fundamental ingredients of reality continue their quiet activity. The emptiest places in the cosmos may therefore be far more dynamic than they appear. As quantum field theory began to mature during the middle decades of the 20th century, physicists encountered an unsettling mathematical problem. The equations worked remarkably well in describing interactions between particles. They successfully predicted how electrons scatter light, how particles interact inside atomic nuclei, and how fields exchange energy through quantum processes. Yet when physicists attempted to calculate certain quantities in detail, something strange happened. The mathematics often produced infinities. Instead of yielding finite answers, the equations sometimes predicted that certain physical quantities should be infinitely large. An electron interacting with its own electromagnetic field, for example, appeared to possess an infinite contribution to its mass. Clearly, this could not be correct. Electrons have measurable masses. Experiments showed precise values. Nature did not appear to contain infinite masses or infinite energies. So the question arose, where were these infinities coming from? At first, many physicists suspected that quantum field theory itself might be fundamentally flawed. A theory producing infinite results might simply be incorrect. However, a group of researchers gradually discovered that the situation was more subtle. The infinities were not necessarily signs that the theory was wrong. Instead, they reflected how the theory behaved at extremely small distances and extremely high energies. In quantum field theory, particles interact not only with other particles but also with the fluctuating fields surrounding them. These interactions include contributions from processes occurring at many different scales. Some contributions arise from relatively large distances. Others arise from interactions occurring at incredibly tiny distances, far smaller than anything that can currently be measured directly. When calculations attempt to include contributions from arbitrarily small distances, the mathematical expressions can grow without bound. This is where the technique known as renormalization enters the story. Renormalization is a method that allows physicists to reorganize the calculations of quantum field theory so that meaningful physical predictions can be extracted from them. Instead of treating quantities such as mass and electric charge as fixed numbers from the beginning, renormalization recognizes that these properties can be influenced by interactions with surrounding fields. In other words, the measured mass of a particle already includes contributions from the quantum fields interacting with it. When physicists perform calculations, they must carefully separate the observable properties of particles from the additional contributions arising within the mathematical description of the theory. By redefining certain parameters in the equations, the infinities can be absorbed into quantities that are not directly observable. What remains are finite predictions that can be compared with experiments. Although this procedure might sound like a mathematical trick, it turns out to work with extraordinary precision. Quantum electrodynamics provides one of the most striking examples. Using renormalization techniques, physicists have calculated the magnetic properties of the electron with astonishing accuracy. The predicted value matches experimental measurements to many decimal places, making it one of the most precise agreements between theory and experiment in the history of science. For many years, however, renormalization was viewed with some suspicion. Some physicists worried that the process seemed artificial, as though infinities were simply being swept aside. A deeper understanding began to emerge during the 1970s through the work of Kenneth Wilson. Wilson introduced the concept known as the renormalization group. Rather than treating renormalization as a mathematical adjustment applied after calculations were complete, Wilson showed that it reflected a deeper physical principle. The key idea was that the laws of physics can appear differently when observed at different energy scales. Imagine studying a complex object through a microscope. At low magnification, the object appears smooth and uniform. At higher magnification, smaller details begin to emerge. With even greater magnification, entirely new structures may appear. Something similar occurs in quantum field theory. At lower energies, certain details of interactions become less important. The behavior of a system can be described using simplified parameters that summarize the combined effects of many smaller processes. As the energy scale increases, those hidden processes become more visible. The parameters describing the system gradually change. The renormalization group provides a mathematical framework describing how physical quantities evolve as the energy scale changes. This insight transformed the understanding of quantum field theory. Instead of viewing the infinities as signs of failure, physicists began to see renormalization as evidence that physical laws possess a layered structure. Different energy scales reveal different aspects of the same underlying system. At everyday energies, the behavior of particles may appear simple and stable. At higher energies, additional interactions emerge, revealing new structures and symmetries. This perspective also explains why certain theories remain predictive even if they are not the final description of nature. A theory may accurately describe phenomena within a particular range of energies, while still being part of a larger framework that becomes relevant at higher energies. In this sense, renormalization teaches an important lesson about scientific knowledge. The laws discovered in physics are often effective descriptions rather than ultimate truths. They work extremely well within specific conditions while hinting at deeper structures waiting to be explored. Kenneth Wilson's work on the renormalization group earned him the Nobel Prize in Physics in 1982. His ideas also influence many areas beyond particle physics. Renormalization methods now play important roles in condensed matter physics, statistical mechanics, and the study of phase transitions. They help explain how collective behavior can emerge from large numbers of interacting components. The concept even appears in studies of critical phenomena, such as the behavior of materials near the point where they change from one phase to another. Through renormalization, physicists gained a new way of thinking about complexity. Instead of focusing only on the smallest possible building blocks, they learned to consider how physical systems behave across many different scales. A phenomenon that appears simple at one scale may arise from intricate interactions at another. In the context of quantum field theory, renormalization reveals a hidden order within the mathematics of fields. What once appeared as a chaotic landscape of infinities now forms a coherent structure connecting different energy scales. The behavior of particles, the strengths of interactions, and the patterns of physical laws all evolve smoothly as the energy scale changes. Seen from this perspective, quantum field theory does more than describe particles. It provides a framework for understanding how the universe organizes itself across layers of scale, from the smallest fluctuations of quantum fields to the structures observed in high-energy experiments. The infinities that once seemed like obstacles ultimately revealed something deeper. They pointed toward the realization that nature may be structured not as a single level of description, but as a hierarchy of physical laws unfolding across different scales of reality. Long before stars began shining and long before galaxies formed their graceful spirals, the universe existed in a state that is difficult to imagine. Temperatures were extraordinarily high, energy densities were immense, space itself was compressed into a region far smaller than the universe observed today. In those earliest moments after the Big Bang, the familiar structures of matter had not yet formed. There were no atoms, no molecules, and no planets or stars. Instead, the universe was dominated by quantum fields. These fields filled space just as they do today, but under far more extreme conditions. The energy contained within them was enormous, and their interactions shape the earliest stages of cosmic history. Understanding this period requires combining ideas from quantum field theory with the study of cosmology, the science of the universe as a whole. One of the most influential developments in this effort emerged during the early 1980s through the work of a physicist named Alan Guth. Guth proposed a bold idea known as cosmic inflation. According to this theory, the universe experienced a brief but extraordinarily rapid period of expansion during its earliest fraction of a second. During inflation, space itself expanded at an astonishing rate, growing from an extremely tiny region to a vastly larger volume in an incredibly short time. Although the exact details remain an active area of research, the central concept suggests that this rapid expansion was driven by a quantum field. This hypothetical field is often called the inflaton field. In this picture, the inflaton field contained a large amount of potential energy during the early universe. That energy caused space to expand exponentially, smoothing out irregularities and producing a universe that appears remarkably uniform on large scales. Inflation helps explain several puzzling features of the cosmos. For example, observations show that the universe appears almost the same in every direction. The temperature of the cosmic microwave background radiation is nearly uniform across the sky. Without inflation, it would be difficult to explain how distant regions of the universe could have reached such similar conditions. Inflation provides a mechanism that spreads energy and matter evenly across vast distances during the early expansion of space. Yet inflation does more than create a smooth universe. It also amplifies tiny quantum fluctuations. Even during inflation, quantum fields could not remain perfectly uniform. As discussed earlier, quantum field theory predicts that fluctuations must always occur. These fluctuations arise from the uncertainty principle and appear as small variations in the energy of fields. During inflation, those tiny fluctuations were stretched dramatically by the rapid expansion of space. A disturbance that originally existed on microscopic scales could become stretched across enormous cosmic distances. Once inflation ended, these stretched fluctuations remained imprinted in the distribution of matter and energy throughout the universe. Over billions of years, gravity gradually amplified those initial irregularities. Regions with slightly higher density attracted more matter, eventually forming the galaxies and galaxy clusters observed today. In this sense, the large-scale structure of the universe may have begun as tiny fluctuations within quantum fields. Galaxies, stars, and even planets may ultimately trace their origins back to small disturbances in fields present during the earliest moments after the Big Bang. Evidence supporting this idea appears in one of the most important observational discoveries in cosmology. In 1965, Arno Penzias and Robert Wilson detected a faint background glow filling the entire sky. This radiation is known as the cosmic microwave background. The cosmic microwave background represents light that has travelled through space since the universe was only a few 100,000 years old. Careful measurements of this radiation reveal extremely small variations in temperature across the sky. These variations are tiny, typically differing by only a few parts in 100,000. Yet those slight differences contain enormous information about the early universe. Modern satellites have mapped these variations with remarkable precision. One of the most detailed measurements was carried out by the Planck satellite mission, operated by the European Space Agency. The Planck mission produced an exquisitely detailed map of the cosmic microwave background, showing the subtle temperature variations across the entire sky. These patterns match the predictions made by inflationary cosmology with striking accuracy. They reveal a universe in which tiny fluctuations in density were present shortly after the Big Bang, providing the seeds from which galaxies later formed. What makes this discovery particularly fascinating is that those fluctuations likely originated from quantum processes, the same type of microscopic fluctuations that appear in quantum fields today may have been stretched to cosmic scales during inflation. In other words, the structure of the observable universe may ultimately trace back to quantum fluctuations occurring in the earliest fractions of a second after the beginning of cosmic time. This connection highlights the profound relationship between particle physics and cosmology. Quantum field theory describes the behavior of fundamental particles and fields at extremely small scales. Cosmology examines the evolution of the universe across distances of billions of light years. Yet these two areas of science meet in the earliest moments of the universe, when quantum fields govern the behavior of all matter and energy. The same theoretical framework used to understand particle interactions inside laboratory experiments also helps explain the distribution of galaxies across the cosmos. This unity of scale is one of the most remarkable aspects of modern physics. Tiny fluctuations occurring within quantum fields may eventually shape the largest structures in the universe. From the delicate patterns observed in the cosmic microwave background to the immense clusters of galaxies stretching across space, the universe appears to carry the imprint of quantum processes from its earliest moments. In that sense, the vast cosmic landscape seen through telescopes may ultimately reflect events that took place at scales smaller than atoms, guided by the behavior of quantum fields during the birth of the universe. Among all the forces described by modern physics, gravity occupies a curious and somewhat stubborn position. On everyday scales, gravity is familiar and reliable. It pulls objects toward the Earth, shapes the orbits of planets, and governs the motion of stars and galaxies across the cosmos. The mathematics describing gravity has been refined for centuries and predicts celestial motion with remarkable precision. Yet when physicists attempt to place gravity within the same framework used to describe other forces, the situation becomes unexpectedly difficult. The challenge arises because gravity is described by a theory very different from quantum field theory. In the early 20th century, Albert Einstein revolutionized the understanding of gravity through his theory of general relativity. Instead of treating gravity as a force acting across space, Einstein proposed that gravity emerges from the geometry of spacetime itself. According to general relativity, mass and energy influence the curvature of spacetime. Objects moving through this curved spacetime follow paths determined by that curvature. What appears to be a gravitational force is actually the result of objects following the natural geometry of spacetime. A simple analogy often used to visualize this idea involves imagining a heavy object placed on a stretched sheet of fabric. The object creates a depression in the sheet, and smaller objects placed nearby roll toward it because the surface has become curved. While the analogy has limitations, it captures the central concept. Gravity reflects the shape of space-time rather than a conventional force transmitted between particles. General relativity has passed many experimental tests. It explains the motion of planets, the bending of light near massive objects, and the existence of gravitational waves traveling through space. Observatories such as the Laser Interferometer Gravitational Wave Observatory, often called LIGO, have directly detected these ripples in spacetime produced by merging black holes and neutron stars. Despite its extraordinary success, general relativity operates in a very different conceptual framework from quantum field theory. Quantum field theory describes nature using quantum fields defined across spacetime. Interactions occur through excitations of those fields and the exchange of particles. General relativity, on the other hand, treats spacetime itself as a dynamic entity that can stretch, curve, and evolve. When physicists attempt to combine these two descriptions into a single theory, serious mathematical difficulties arise. One approach involves attempting to describe gravity as another quantum field. In this view, gravitational interactions would be carried by a particle known as the graviton. The graviton would represent the quantum of the gravitational field, similar to how photons represent the quantum excitations of the electromagnetic field. If gravitons exist, they would possess very specific properties. They would carry no electric charge, travel at the speed of light, and have a property known as spin equal to 2. Their interactions would reproduce the familiar gravitational behavior described by general relativity at large scales. Early attempts to explore this possibility were carried out during the 1960s and 1970s by several researchers working on quantum gravity. One important figure in this effort was Bryce DeWitt. DeWitt developed mathematical techniques aimed at applying quantum principles to the gravitational field. His work explored how spacetime geometry might behave when treated as a quantum system. Other physicists, including John Wheeler, contributed to the development of related ideas. Wheeler introduced imaginative concepts such as spacetime foam, suggesting that at extremely small scales, the geometry of spacetime might fluctuate wildly due to quantum effects. These ideas hinted that spacetime itself might possess a complex microscopic structure, shaped by quantum processes. However, when physicists attempted to apply the same renormalization techniques that succeeded in other quantum field theories, they encountered serious obstacles. In ordinary quantum field theories, infinities appearing in calculations can often be controlled through renormalization. The resulting theories remain predictive and consistent. Gravity behaves differently. When treated as a quantum field, gravity produces mathematical divergences that cannot easily be removed using standard renormalization techniques. Each attempt to calculate quantum corrections introduces additional infinities requiring new adjustments. This process quickly becomes unmanageable. The difficulty arises partly because gravity interacts with energy itself. Any fluctuation in energy contributes to the gravitational field, and quantum fields constantly fluctuate. As a result, gravity becomes sensitive to processes occurring at extremely small distances, where the structure of space-time may no longer resemble the smooth geometry described by general relativity. Many physicists believe that a deeper theory must exist that unifies gravity with the principles of quantum mechanics. Several candidate approaches have been proposed. One well-known framework is string theory, which suggests that fundamental particles are not point-like objects, but tiny vibrating strings. In string theory, one of the vibrational modes naturally behaves like a graviton. Another approach, known as loop quantum gravity, attempts to quantize spacetime itself. In this theory, space may be composed of discrete units, forming a network of interconnected loops. Both approaches aim to reconcile the geometric description of gravity with the probabilistic nature of quantum mechanics. Despite decades of research, however, no single theory of quantum gravity has yet achieved the same experimental confirmation as the standard model of particle physics. This remains one of the greatest open challenges in modern physics. Understanding quantum gravity may reveal what happens inside black holes, how space-time behaves at the smallest possible scales, and what occurred during the earliest moments after the Big Bang. It may also explain whether spacetime itself emerges from deeper quantum structures. For now, gravity stands somewhat apart from the other forces described by quantum field theory. The electromagnetic force, the weak nuclear force, and the strong nuclear force all fit comfortably within the framework of quantum fields. Gravity, by contrast, continues to resist complete integration into that picture. This tension between general relativity and quantum mechanics serves as a reminder that even the most successful theories may represent only part of a larger story. Somewhere within the mathematics of fields and spacetime, a deeper understanding of gravity may still be waiting to be discovered. By the late 20th century, the standard model of particle physics had become one of the most successful scientific theories ever constructed. It explained the behavior of known fundamental particles. It predicted new particles that were later discovered in experiments, and it provided calculations that matched experimental measurements with extraordinary precision. Yet despite its success, physicists gradually realized that the standard model was not the final word on the structure of reality. It works remarkably well within the energy ranges explored so far, but it leaves several profound questions unanswered. One of those questions involves the relationship between different types of particles. In the standard model, particles fall into two broad categories known as fermions and bosons. Fermions include the particles that make up matter, such as electrons, quarks, and neutrinos. These particles obey a rule known as the Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state. Bosons, on the other hand, are particles that carry forces. Photons transmit the electromagnetic force. Gluons carry the strong nuclear force. The W boson and the Z boson transmit the weak nuclear force. The Higgs boson represents an excitation of the Higgs field. The mathematical properties of fermions and bosons are fundamentally different. They follow distinct statistical rules and behave in contrasting ways. This sharp division between the two types of particles led some physicists to wonder whether a deeper symmetry might connect them. One proposal that emerged during the 1970s is known as supersymmetry. Supersymmetry suggests that every fermion might have a corresponding boson partner, and every boson might have a corresponding fermion partner. In this framework, particles that appear very different at first glance may actually belong to pairs connected by a hidden symmetry. The early mathematical foundations of supersymmetry were developed by theorists including Julius Wess and Bruno Zumino. Their work demonstrated that certain quantum field theories could possess a symmetry, transforming fermions into bosons and bosons into fermions while preserving the overall structure of the equations. If supersymmetry exists in nature, it would imply the existence of many new particles. For example, the electron might possess a partner particle called the selectron. Quarks could have partners known as squarks. Photons might have partners called photinos. These names may sound unusual, but they follow a systematic pattern reflecting the symmetry between particle types. One reason supersymmetry attracted attention is that it could help solve several theoretical puzzles. For instance, it may help stabilize the mass of the Higgs boson against large quantum corrections. Without additional mechanisms, calculations in quantum field theory suggest that the Higgs mass could be extremely sensitive to very high energy physics. Supersymmetry introduces new particles whose contributions can cancel certain problematic effects, helping maintain the observed mass of the Higgs boson. Another intriguing possibility involves dark matter. Astronomical observations reveal that visible matter represents only a small fraction of the total mass in the universe. Galaxies rotate faster than expected, and clusters of galaxies exhibit gravitational effects that cannot be explained by ordinary matter alone. The missing mass responsible for these effects is known as dark matter. Dark matter does not emit light and interacts only weakly with ordinary matter. Yet its gravitational influence appears throughout the universe. Some supersymmetric theories predict stable particles that could serve as candidates for dark matter. If such particles exist, they may fill the universe as a new type of invisible matter interacting primarily through gravity. Supersymmetry is not the only idea proposed to extend the Standard Model. Another possibility involved the hypothetical particle known as the axion. The axion emerged from an attempt to solve a puzzling issue within quantum chromodynamics known as the strong charge parity problem. This problem concerns why certain interactions predicted by the equations of quantum chromodynamics do not appear to occur in nature. In the late 1970s, Roberto Peccei and Helen Quinn proposed a theoretical mechanism that could explain this absence. Their idea introduced a new symmetry, now known as the Peccei-Quinn symmetry. When this symmetry is incorporated into quantum field theory, it predicts the existence of a new particle called the axion. Axions would interact extremely weakly with ordinary matter and could exist in enormous numbers throughout the universe. Because of these properties, axions have become another leading candidate for dark matter. If axions exist, they would represent excitations of a new quantum field permeating space, similar in concept to other fields already known in particle physics. Detecting axions, however, is extremely challenging. Experiments searching for axions often involve sensitive detectors designed to observe tiny interactions between axions and electromagnetic fields. Several research collaborations around the world are currently searching for evidence of these particles. Meanwhile, large particle accelerators continue probing higher energy scales in hopes of discovering new physics beyond the Standard Model. Facilities such as the Large Hadron Collider at CERN accelerate particles to tremendous energies and examine the results of their collisions with exquisite precision. These experiments search for deviations from the predictions of the Standard Model that might reveal the presence of previously unknown particles or forces. So far, the Standard Model has remained remarkably resilient. The discovery of the Higgs boson confirmed one of its final major predictions, but no clear evidence for supersymmetry or other extensions has yet appeared. Still, physicists continue exploring these possibilities with patience and curiosity. The history of science often shows that new discoveries emerge when experimental techniques reach greater precision or when observations extend into new energy ranges, it is entirely possible that additional quantum fields and particles remain hidden just beyond the current limits of detection. If such discoveries occur, they may reveal deeper symmetries underlying the universe. They may explain the nature of dark matter, illuminate the earliest moments of cosmic history, or provide clues about how gravity might eventually fit into the framework of quantum theory. For now, the Standard Model stands as a powerful yet incomplete map of the quantum world. Beyond its boundaries, new ideas continue to explore the possibility that the universe contains fields and particles still waiting to be discovered. For much of the 20th century, physics developed two powerful but somewhat separate descriptions of reality. One description is quantum field theory, which explains the behavior of particles and forces through fields that fill the universe. The other description is general relativity, Albert Einstein's theory in which gravity emerges from the curvature of space-time. Each theory has been extraordinarily successful in its own domain. Quantum field theory describes the microscopic world of particles with astonishing precision. General relativity explains the motion of planets, the behavior of black holes, and the large-scale evolution of the universe. Yet when physicists look more closely, the boundary between these two descriptions begins to blur. The reason is that quantum fields exist within space-time, but they may also influence the structure of space-time itself. In everyday situations, this influence is extremely small. The energy contained in quantum fluctuations usually has negligible gravitational effects. But when physicists examine extreme environments such as black holes or the earliest moments of the universe, the interaction between quantum fields and space-time becomes impossible to ignore. One of the most important researchers exploring this connection was Stephen Hawking. In the 1970s, Hawking investigated what happens when quantum fields are studied near the boundary of a black hole. According to classical general relativity, a black hole possesses an event horizon, a surface beyond which nothing can escape. Once matter crosses this boundary, it can never return to the outside universe. However, Hawking realized that quantum field theory changes this picture. Because quantum fields fluctuate even in empty space, particle pairs can briefly appear near the event horizon. Under certain conditions, one particle from such a pair can fall into the black hole, while the other escapes into space. To an outside observer, this process appears as radiation emerging from the black hole. This phenomenon is now known as Hawking radiation. The remarkable implication is that black holes are not completely black. Over extremely long timescales, they may slowly lose energy through this quantum process. Hawking radiation provided one of the earliest clues that quantum fields and space-time geometry are deeply intertwined. Another important contribution to this subject came from the Soviet physicist Yakov Zeldovich. Zeldovich studied how vacuum energy might influence the large-scale behavior of the universe. As discussed earlier, quantum field theory predicts that even empty space contains fluctuating fields. These fluctuations imply that the vacuum possesses energy. If vacuum energy exists, it should contribute to the gravitational dynamics of the universe. In Einstein's equations of general relativity, there is a term known as the cosmological constant. This term represents a form of energy associated with empty space itself. The cosmological constant was originally introduced by Einstein as a way to produce a static universe, although he later abandoned the idea after the discovery that the universe is expanding. However, quantum field theory brought the concept back into focus. Calculations of vacuum energy suggested that empty space should possess an enormous amount of energy due to the fluctuations of quantum fields, The problem is that the predicted value from quantum field theory is vastly larger than what observations allow. Astronomical measurements indicate that the universe is expanding at an accelerating rate. This acceleration can be explained by a small positive cosmological constant or a similar form of energy often called dark energy, yet the value required to match observations is incredibly tiny compared with the vacuum energy predicted by naive calculations in quantum field theory. This discrepancy is known as the cosmological constant problem. It is one of the most significant unsolved puzzles in modern physics. The difference between the predicted and observed values is enormous, involving a mismatch of many orders of magnitude. Physicists continue searching for an explanation that might reconcile these numbers. Some researchers believe the solution may involve new symmetries in quantum field theory. Others suspect that the vacuum energy predicted by current theories is incomplete or misunderstood. Another possibility is that space-time itself may not be fundamental. In recent decades, several theoretical approaches have suggested that space-time could emerge from deeper quantum structures. One idea proposes that space-time might arise from patterns of quantum entanglement between microscopic degrees of freedom. Another approach explores whether space-time geometry could emerge from networks of quantum information, somewhat like the way a complex pattern can emerge from many simple elements interacting together. In these models, space-time may behave more like a collective phenomenon, rather than a basic ingredient of reality. Just as the smooth surface of a lake emerges from the motion of countless water molecules, the geometry of space-time might emerge from the interactions of deeper quantum systems. Quantum field theory may therefore be part of a larger framework that includes both fields and space-time as aspects of a more fundamental structure. If such ideas prove correct, the distinction between fields and space-time could dissolve. Fields would not merely exist within space-time. Instead, both fields and space-time might arise together from underlying quantum relationships. Although these ideas remain speculative, they reflect a growing recognition that the universe may be organized in ways that challenge traditional categories. The stage and the actors may not be separate. Space-time may not simply provide the arena where quantum fields operate. Instead, the geometry of space and time could be intimately connected with the fields themselves. Understanding this relationship remains one of the deepest goals in modern physics. It may require new mathematical frameworks, new experimental insights, and perhaps entirely new ways of thinking about the nature of reality. For now, the study of quantum fields continues to reveal that the universe is far more structured than it first appears. Even the emptiest regions of space may contain layers of hidden complexity, linking the behavior of quantum fields with the fabric of space-time itself. As the 20th century progressed, quantum field theory became one of the most successful tools in all of physics. It described particles, predicted new phenomena, and produced calculations that matched experiments with astonishing accuracy. Yet success often leads to new questions. Once physicists understood the basic structure of quantum fields, they began exploring ideas that reached far beyond the original framework. Some of these ideas sounded almost philosophical at first glance, but they were grounded in serious mathematical work and careful physical reasoning. These developments began to push the boundaries of how fields, space-time, and reality itself might be connected. One important step in this direction involved a class of theories known as conformal field theories. The foundations of conformal field theory were developed through the work of several researchers, including the Russian physicist Alexander Polyakov. A conformal field theory is a quantum field theory with an additional type of symmetry known as conformal symmetry. This symmetry means that the theory remains unchanged even when distances are stretched or compressed in certain ways, as long as the angles between directions remain the same. While this may sound abstract, conformal symmetry turns out to be extremely powerful. It places strong constraints on how fields can behave and allows physicists to analyze systems that would otherwise be mathematically intractable. Conformal field theories have found applications in many areas of physics. They appear in the study of phase transitions in condensed matter systems, in statistical mechanics, and in high-energy particle physics. In some situations, these theories describe systems that behave in the same way across many different scales. Such systems are said to possess scale invariance. Scale invariance means that the system looks similar whether it is examined at large distances or extremely small ones. This property turns out to be deeply connected with the renormalization ideas discussed earlier, where physical laws can change depending on the energy scale being examined. During the 1970s and 1980s, physicists began noticing surprising connections between conformal field theories and gravitational physics. One of the key insights that emerged from this work involved a radical proposal about how information might be stored in the universe. This proposal became known as the holographic principle. The holographic principle was first suggested by the Dutch physicist Gerard 't Hooft and later developed further by Leonard Susskind. The idea arose partly from studies of black hole thermodynamics. Research by Stephen Hawking and Jacob Bekenstein had shown that black holes possess entropy proportional to the area of their event horizons rather than the volume of the region they contain. Entropy is a measure of information or microscopic complexity within a physical system. The surprising implication was that the information describing everything inside a black hole might be encoded on its surface. This observation inspired the broader idea that the information contained within a region of space might be fully described by degrees of freedom located on its boundary. In other words, a three-dimensional region of space might be equivalent to a two-dimensional description on its surface. The analogy with a hologram gave the principle its name. In a hologram, a two-dimensional surface can encode a three-dimensional image. Similarly, the holographic principle suggests that a lower-dimensional description might encode the physics of a higher-dimensional region of space. Although this idea initially seemed almost philosophical, it gained strong mathematical support through a discovery made in the late 1990s. In 1997, the Argentine physicist Juan Maldacena proposed a remarkable relationship known as the anti-de Sitter conformal field theory correspondence, often called the AD-CFT correspondence. Maldacena suggested that a particular gravitational theory, defined in a higher dimensional spacetime, could be exactly equivalent to a conformal field theory defined on the boundary of that spacetime. This proposal created a bridge between two very different descriptions of physics. On one side of the correspondence is a theory of gravity living within a curved spacetime. On the other side is a quantum field theory without gravity defined on the boundary of that space. If the correspondence holds, calculations performed in one description can be translated into results within the other. This duality has become one of the most influential ideas in theoretical physics. Although the specific spacetime used in the correspondence does not match the geometry of our universe exactly, the underlying concept has provided new ways of studying quantum gravity and strongly interacting quantum field theories. Researchers have used the AD-CFT correspondence to investigate problems in nuclear physics, condensed matter physics, and quantum information theory. The correspondence suggests that spacetime geometry may be closely related to patterns of quantum information within field theories. In the recent years, some physicists have proposed that spacetime itself may emerge from the entanglement structure of quantum systems. Quantum entanglement is a phenomenon in which particles become linked in such a way that the state of one cannot be fully described without reference to the other, even if they are separated by large distances. Entanglement plays a central role in quantum mechanics, and it also appears naturally within quantum field theories. Researchers have begun exploring whether networks of entangled quantum states could generate structures resembling spacetime geometry. In these approaches, spacetime may not exist as a fundamental entity. Instead, it could arise as a large-scale manifestation of relationships between underlying quantum degrees of freedom. This idea remains speculative, but it has attracted considerable attention because it offers a possible path toward understanding quantum gravity. It also illustrates how far modern physics has moved from the classical view of particles moving through empty space. Quantum field theory originally described particles as excitations of fields filling the universe. Now, some researchers are considering the possibility that even space-time itself might emerge from deeper layers of quantum structure. These radical ideas demonstrate how the study of quantum fields continues to expand the conceptual boundaries of physics. What began as a mathematical framework for describing particle interactions has evolved into a tool for exploring the deepest questions about the nature of space, time, and information. As research continues, the relationship between quantum fields, geometry, and information may reveal new insights into the fundamental architecture of reality. And although many of these ideas remain theoretical, they remind physicists that the universe may still hold surprises waiting far beyond the limits of current understanding. When physicists first began studying atoms and radiation, the universe appeared to be built from tiny objects. Electrons orbited atomic nuclei, photons carried light, protons and neutrons formed the cores of atoms. These particles seemed like the fundamental ingredients of reality. For many decades, this picture felt natural. The world appeared to consist of small objects interacting through forces acting between them. Yet as the 20th century progressed, a different understanding gradually emerged. Quantum field theory revealed that particles may not be the most fundamental elements of nature after all. Instead, particles appear to be excitations of deeper structures known as fields. A useful image is that of waves on the surface of an ocean. When watching waves rolling across the sea, it may appear as though the waves themselves are objects moving across the water, but the waves are not independent objects. They are disturbances within the water itself. Quantum field theory suggests that particles behave in a similar way. The universe contains many different fields extending throughout all of space. The electron field fills the cosmos. The electromagnetic field fills space as well. The quark fields, the gluon field, and the Higgs field all exist everywhere simultaneously. When these fields are gently disturbed, they produce localized excitations. Those excitations are what physicists observe as particles. An electron is therefore not a tiny solid object flying through space. It is a ripple within the electron field. A photon is a ripple in the electromagnetic field. A Higgs boson is a ripple within the Higgs field. From this perspective, the universe resembles an intricate network of interacting fields, rather than a collection of separate particles. These fields overlap throughout space, constantly interacting with one another according to the laws described by quantum field theory. The concept may initially feel abstract, but it leads to extremely precise predictions. One example comes from the study of the strong nuclear force. In the early 1970s, physicists David Gross and Frank Wilczek, along with David Politzer working independently, discovered an important property of the theory describing the strong interaction. This property is known as asymptotic freedom. asymptotic freedom describes how quarks behave when they approach extremely high energies or extremely short distances. In everyday conditions, quarks are tightly bound together inside protons and neutrons by the strong nuclear force. This force is carried by particles called gluons, which represent excitations of the gluon field. However, Gross, Wilczek, and Politzer discovered that the strength of the strong force changes depending on the distance between quarks. At very short distances, the interaction between quarks becomes weaker. Quarks begin to behave almost like free particles. At larger distances, the force becomes stronger and pulls quarks back together. This behavior explained results observed in high-energy particle experiments and provided strong support for quantum chromodynamics, the quantum field theory describing the strong nuclear force. The discovery of asymptotic freedom earned Gross, Wilczek, and Politzer the Nobel Prize in Physics in 2004. Their work demonstrated once again how quantum field theory can reveal subtle patterns hidden within the fundamental forces of nature. The predictive success of quantum field theory extends far beyond this single example. Quantum electrodynamics, which describes interactions between electrons and photons, produces predictions that match experiments with astonishing precision. Measurements of the magnetic properties of the electron agree with theoretical calculations to an accuracy that reaches many decimal places. Few scientific theories in history have achieved such precise agreement between mathematics and observation. Despite this success, quantum field theory remains conceptually unusual. It describes a universe where what appears to be empty space actually contains a complex structure of interacting fields. Particles emerge as temporary patterns within those fields. Even the vacuum itself is not truly empty. Quantum fluctuations continually ripple through the fields that fill the universe. Virtual particles briefly appear and vanish. Vacuum energy contributes to the dynamics of space-time. The emptiest regions of the cosmos may therefore contain some of the most subtle activity in all of nature. This realization carries profound philosophical implications. For centuries, the idea of emptiness suggested the absence of physical reality. Empty space seemed like a simple backdrop against which events unfolded. Quantum field theory overturns that intuition. Instead of being a passive stage, the vacuum becomes an active participant in the behavior of the universe. Fields exist everywhere. Their fluctuations shape the properties of particles, influence the evolution of the cosmos, and may even contribute to the expansion of space-time itself. The objects encountered in everyday life are therefore built from patterns within fields that extend across the entire universe. The atoms in a rock, the molecules in the air, and the cells in a living organism all arise from excitations of fields interacting according to quantum principles. From this perspective, matter appears less like solid substance and more like organized activity within an underlying network of fields. Although the mathematics describing these ideas can be complex, the central picture is surprisingly elegant. Reality may consist of a collection of fields filling space, each capable of producing particles when disturbed. Those fields interact with one another according to precise rules, forming the structure of the physical world. The remarkable success of quantum field theory suggests that this framework captures something deeply true about the universe. And yet, many mysteries remain. Gravity has not yet been fully integrated into the quantum field framework. Dark matter and dark energy continue to challenge current theories. New fields and particles may still await discovery, but one lesson has already become clear. What once appeared to be empty space is anything but empty. It may be the most active and fundamental part of reality. The quiet vacuum surrounding every object could be filled with invisible fields, subtle fluctuations, and hidden structures shaping the universe at every moment. And in that silent activity, the deepest architecture of the cosmos may quietly unfold,